NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Pluto, a far-off and cryptic planet, was once viewed as a component of our neighborhood planetary framework. However, late, astonishing proclamations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have pushed Pluto back into the spotlight. They suggested that this cold world may be on a potential impact course with Neptune. How might this be within the realm of possibilities? And what results would such a horrendous occasion have? Could this be a captivating, grandiose irregularity? Or is there something more to this approaching debacle? Join us as we dig into the potential outcomes of a Pluto-Neptune crash. Once classified as a planet and later renamed as a dwarf planet, Pluto remains a subject of interest in the vast universe. This is evident from the recent hypotheses by prestigious specialists. Pluto's orbit closely intersects with Neptune's, which has raised concerns among astrophysicists, including Neil deGrasse Tyson and Michio Kaku, who warn of a possible unfortunate impact between the two with significant repercussions for Earth. But how could such an event occur? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires a staggering 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not yet completed a full revolution. The intrigue doesn't end there. Pluto's orbit is extraordinarily eccentric, deviating greatly from the nearly circular orbits of the major planets. A particularly fascinating feature is its tilt, 17 degrees to the ecliptic plane, making its path noticeably slanted compared to other planets. This inclination and irregularity add additional layers of complexity to its orbit. One of the most exceptional aspects of Pluto's orbit is how it converges with Neptune's. For about 20 years during each orbit, Pluto comes closer to the Sun than Neptune, defying what one might expect based on their positions in the planetary system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions of other planets. The study of Pluto's orbit began following its discovery as astronomers sought to understand its unique path. Unlike most planets whose orbits lie close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and unusual shape. The mystery deepened as scientists realized that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit, despite these complexities, demonstrates the intricacies of celestial mechanics. The three-body problem in space refers to the challenge of calculating how three objects in space, like Pluto, Neptune, and the Sun, interact gravitationally. This is akin to predicting where objects will move based on their initial positions and mutual gravitational influences. In Pluto's case, the issue shows how its orbit, Neptune's, and the Sun's gravity all interact in a complex manner. Astrophysicists highlight terms like asynchronous libration, orbital precession, and the VZK oscillation to explain this phenomenon. Asynchronous libration refers to how, whenever Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune. This spatial separation is crucial to preventing a collision. Orbital precession refers to the slight vertical movement of a celestial body. For Pluto, this means that when it approaches Neptune or another massive planet, it is positioned above their orbital plane, providing an additional protective measure. VZK oscillation describes how Pluto, Neptune, and the Sun's gravitational forces influence each other. This oscillation helps stabilize Pluto's orbit, preventing irregular movements that could lead to a collision. Despite Pluto's seemingly unpredictable path, This oscillation stabilizes its movement over long periods, revealing that even chaotic-seeming systems follow hidden patterns and rules. These factors help keep Pluto's orbit stable, ensuring that it doesn't collide with Neptune or drift too far off course. The three-body problem is crucial for understanding the changes in these orbits and the interactions between celestial objects. Studying this helps scientists learn more about Pluto, our solar system, and even distant stars and planets. Numerical simulations during the 1980s revealed that, despite these stabilizing effects, Pluto's orbit is chaotic. Even small variations in its initial conditions could lead to significant changes over centuries. Nevertheless, Pluto's orbit has been found to maintain stability over very long time scales. Further studies have helped us understand how Neptune, Jupiter, and Saturn influence Pluto's orbit. There is a unique resonance relationship between Neptune and Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. Jupiter's massive gravity also plays a critical role in stabilizing Pluto's orbit, preventing it from straying too far into Neptune's domain. Saturn's gravitational pull adds another layer of stability. These findings suggest that Jupiter, Saturn, and Neptune work in tandem to ensure Pluto's safe passage through space without encountering significant issues. Without these gravitational interactions, the solar system could be a much more chaotic place, where objects like Pluto might collide with other planets or be ejected from their orbits, triggering a cascade of events. For Pluto, understanding its orbit is essential, particularly with discussions about the possibility of it colliding with Neptune in the future. This also gives us a clearer understanding of the dynamic nature of the nearby planetary system. The case of Pluto highlights how even the most seemingly unstable orbits can reach a state of balance through the intricate interplay of gravitational forces. The lessons drawn from Pluto's orbit extend far beyond its own peculiarities. They provide valuable insights into the mechanics of celestial bodies throughout the universe. These principles guide astronomers and astrophysicists in studying exoplanetary systems, star formations, and the potential for life in other parts of the cosmos. The extraordinary balance maintained in Pluto's orbit demonstrates that even the most complex and seemingly chaotic systems can achieve long-term stability. This revelation underscores the power of gravitational forces and resonance relationships, which orchestrate the movements of celestial objects in a harmonious cosmic dance. However, the idea of a potential Pluto-Neptune collision, as suggested by some speculative models, continues to provoke discussion and debate among scientists and the general public. If such a catastrophic event were to occur, it would not only affect these two celestial bodies but could also disrupt the orbits of other planets, creating ripples of instability across the solar system. While the likelihood of such a collision is extremely low due to the factors described above, the very thought of it forces scientists to re-examine long-held assumptions about orbital mechanics and gravitational interactions. This ongoing study highlights the importance of refining our models and simulations to account for even the smallest variables that could influence planetary orbits over vast timescales. For now, Pluto remains on its distant, icy path, a testament to the wonders of celestial mechanics. Its peculiarities continue to challenge and inspire scientists, serving as a reminder of the vast, intricate, and often unpredictable nature of our universe. In conclusion, the potential collision between Pluto and Neptune, while fascinating to contemplate, is far more a question of theoretical interest than immediate concern. What remains undeniable is that Pluto's unique orbit and its relationship with other celestial bodies offer a wealth of knowledge about the delicate balance that governs the cosmos. As we look to the future, these insights will undoubtedly shape our understanding of the universe and our place within it. Orbital mechanics likewise highlight the significance of consistent perception and research to better grasp our place in the universe. The investigation of celestial bodies frequently leads us to confront their peculiar behaviors, and Pluto's orbit is a perfect example of this strange nature. The idea of orbital chaos, which refers to the sensitivity of a celestial body's orbit to its initial conditions, is clearly demonstrated by Pluto's path. Even slight changes in its position or speed can lead to dramatic shifts in its long-term orbit. Automated simulations have been instrumental in helping researchers understand Pluto's movements in space. These simulations use advanced mathematics to model the gravitational interactions between Pluto, Neptune, and other bodies in the solar system. By tweaking small details in the simulations, scientists can see how even minor shifts can significantly alter Pluto's trajectory. In the late 1980s, these simulations revealed fascinating insights about Pluto's orbit. While stabilizing factors like non-synchronous libration and orbital precession help maintain its stability, Pluto's orbit can still be irregular if its initial conditions vary even slightly. However, despite the apparent chaos, Pluto's orbit remains stable over extensive timescales, such as billions of years. This suggests that, despite the seeming eccentricity of Pluto's journey around the Sun, there is an underlying order to it. Predicting the movements of celestial bodies, particularly those with irregular orbits like Pluto, is a massive challenge. The inherent unpredictability of these systems means that long-term predictions are fraught with uncertainties. While mathematical models are invaluable in understanding and forecasting the future movements of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions, and even the smallest error can lead to vastly different outcomes. The chaotic nature of planetary orbits, such as Pluto's, serves as a reminder of the ever-changing and dynamic nature of the universe. While we have made incredible progress in understanding space, Pluto's case shows how much there is still to discover. The gravitational effects of the giant planets on Pluto's orbit provide significant insights into the broader workings of the solar system. They reveal how the positioning of each planet can greatly influence the stability and trajectory of other bodies within the system. So why have prominent astrophysicists recently raised concerns about a potential collision between Pluto and Neptune? Despite the many forces working to keep the two planets from colliding, Neil deGrasse Tyson, a leading astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly Pluto. Tyson, who played a role in Pluto's reclassification as a dwarf planet, provides valuable insights into the evolving understanding of celestial mechanics and the public's renewed interest in overlooked aspects of space. Tyson sees the reclassification of Pluto not as a demotion but rather as a necessary change based on the expanding knowledge of the various objects orbiting the Sun. He believes that the complexities of orbits like Pluto's reflect how much is still left to explore in space. The ongoing fascination with these questions fuels the excitement of space exploration. Despite Tyson's optimism, his concerns about Pluto's potential collision with Neptune suggest that there are still many unknowns regarding Pluto's orbit. Will Pluto collide with Neptune, or is this just another instance of confusion in the ever-changing universe? Only time and further research will provide an answer. For now, we are left with an increased curiosity about how little we truly know about our own solar system. We continue to study these celestial phenomena with the aim of uncovering the secrets that lie beyond. The possibility of a Pluto-Neptune collision raises further questions about the mysterious and fascinating universe in which we live. The idea of an impact between Pluto and Neptune challenges our conventional understanding of planetary stability, especially given the current relative stability of their orbits. Given Pluto's location on the outer edges of the solar system, far from the major planets, and Neptune's status as a gas giant with a powerful gravitational field, the implications of such a collision would be significant for our understanding of gravitational interactions and the solar system's evolution. To comprehend the dynamics of a potential collision, one must first consider the composition and properties of Pluto and Neptune. Pluto, despite being a dwarf planet, is composed of various substances believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere consists primarily of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is made mostly of hydrogen, helium, and other lighter elements, with a dense, deep atmosphere. A collision between these vastly different bodies would significantly alter their structure and behavior, potentially creating an event visible across great distances. What makes this hypothetical impact particularly intriguing is the influence of other bodies in the solar system. While Neptune's gravity plays a key role in stabilizing Pluto's orbit, it is not the only factor at play. Jupiter, with its immense mass and strong gravitational force, also stabilizes Pluto's orbit, preventing it from drifting too close to Neptune. Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. However, despite the apparent risks, ongoing research has shown that the relationship between Pluto and Neptune is far more complex than a straightforward collision course. The gravitational resonance between Pluto and Neptune, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a harmonic lock that prevents them from directly colliding. This resonance is a crucial factor in ensuring that Pluto and Neptune's orbits, while they intersect in the vastness of space, have never resulted in a direct impact.